recording. Okay, now we're recording. All right. And we're going to go back to our PowerPoint. This is good. And we're going to start. Okay, so where we left off last time was talking about matching the feed to user preferences and the fact that Facebook would rather observe what people are interested in than ask them. Okay, because observation works better. So, other stuff. When Facebook is organizing the feed, obviously they want to show you more recent, right? All else equal, they want to show you more recent posts, more recent ads. In general, that's going to be a better reflection of your current interests and current interactions, right? When they're looking back through your history, they're going to say, whatever you've looked at in the last 2, 3, maybe 10, 15 years, they're going to emphasize the more recent stuff. Okay, so for example, you're at an age where your musical tastes have probably changed dramatically in the last 5 or 10 years. Probably most of you don't like all the same stuff you did, when you were a tween. Whereas, you reach a certain age like mine, and your stuff is maintained fairly flat for the last, 10 or 20 years. You like the same kind of stuff you like. So that's the trade-off. For some people, sure, their tastes are going to change pretty quickly over the years. Others not so much. The downside of using a smaller sample size is there going to be more estimation errors. For example, suppose Facebook is only looking at like a week stretch of your history to determine what you're interested in. Well, what if during the course of that 1 week, your little brother got hold of your Facebook account and clicked on a bunch of random stuff, right? That's going to throw it all off a lot more than it would if Facebook is looking at, say, a year's worth of data. So there's some kind of happy medium in there. Facebook does want a reasonably long window that encompasses your interests, but they don't want to have it be too short either, right? So that's the trade-off. They want it long enough to capture a good range of data, but not so long that it captures a lot of irrelevant data. Other stuff. Facebook is going to update the feed for every single new interaction, right? Every time you do some new little thing, Facebook isn't going to recalculate its entire algorithm for you. Instead, what it's going to do, it's going to do some kind of batch update at the end of the day. It'll say all the things you did. It's going to update your profile, and it's going to include that the next time around it builds your feed. And, the simple thing is, typically over the course of the day, if your preferences are consistent, it's not going to change them instantly. Okay. Now, within all the stuff that we've talked about how Facebook constructs the feed and how they assess your interests and how they show you what they're going to show you, there's a lot of wiggle room for devising policies, right? We still have these 3 general principles. Facebook wants to show you the kind of content that you're interested in. It wants to show you the content from the people that you're most interested in, and it wants to show you more recent data, right? But there's still a lot of questions that they have to resolve to make the algorithms work well for everybody. So things like, what if somebody is an infrequent user, right? What if somebody only logs in once every week? Should they, pretty much ignore all the stuff that's 2 to 6 days ago and mostly only show you the 1 day? No, probably not, right? They probably want to give extra consideration to a little bit older posts because they're still going to be new to you. Second one, how should posts time out, right? So even if we accept that older posts should get pushed down to the bottom of the stack eventually, the question is, how quickly should they be pushed down, right? So for example, sometimes you'll log into Facebook a couple times within an hour and not much is going on, and you'll see the same few posts at the top of your feed. Yeah, I mean, that can go on for a little while, but eventually there's going to be some turnover and they'll get pushed back down. Question is, should they ever come back if they turn out that they were popular, and how quickly should they be pushed down? Other stuff, should they accept money for advertisers who want to get a better position in the feed? The short answer is yes. Yes, they should probably accept that money. Other things, duplicate viral posts from a user's friend. So sometimes you're on Facebook and you'll see like 2 or 3 or more people have all echoed the same post, and it's like you want to pick one of them to interact with. You don't want to interact with all of them, right? Because then that's kind of a doofus thing to do. But on the other hand, sometimes you don't want to pick a particular one and leave the other ones out. What else? Things like reactions versus likes. Okay, so lately, what was it? A couple years ago, Facebook put up some extra interactions, like the care. That was not that long ago. Some of the other ones too. The wow reaction. Some of those. How should those be weighted versus likes, right? Should they count the same? Should they count more? Should they count less? And other stuff, how should Facebook absorb feedback? For example, things like spam posts or ads from infected servers, right? So if there's some bad guys, they post an ad through Facebook, but they try to, or an article through Facebook, some bad guys attack the server, and now when you go to look at that article, they try to put some malware on your machine. How does Facebook manage that? So all these security type issues and content control issues, those aren't really held within Facebook's simple algorithm either. So my point is not to give answers to any of those, but just to say, yeah, you figured out a ranking system, but that doesn't really solve, all the problems. There's still a lot more policy decisions for Facebook to make. Okay. User control, right? So the question is, if you were going to ask people what sort of things they were interested in, right? So for example, if you were going to have a massive list of checkboxes and users would check off the topics that they were interested in, or they were going to write up a set of keywords, like 10 or 20 keywords describing things they were interested in, how well would that work? Well, problem is it doesn't at that level of variety of content. So number one, Facebook, in order to give you a list of things that's actually manageable, right? They're not going to give you a list of 10,000 topics. So they're going to grab them all together, right? It'll be something like, instead of particular bands, right? They might have a few music bands, but mostly they're going to say, are you interested in music? And then, give categories for that. That's probably the best they're going to do. Another one, what about interest in a niche topic? So for example, I have a second cousin by the name of Brock Lundquist, who last I checked was in AA trying to play baseball for the Toronto Blue Jays. Now, I don't have that much interest in baseball. I mean, I'll watch the Cubs if they're in the playoffs. If the Sox were in the playoffs, I might even watch them. But otherwise, don't have that much interest in baseball, and certainly not that much in American League or, a team in Toronto. However, if my second cousin got signed by them, yeah, I'd probably watch a bunch of those games, at least for the first year or so. So I don't have a huge interest in the overall topic, but I do have a tiny limited interest in this area. And that sort of thing, again, is very difficult to capture in this sort of checkbox type list. Last one is imprecise post tagging, right? So how do you make sure that the people who are categorizing the content actually do a good job with it? Again, if it's a big category like politics or business news or, I don't know, films, whatever, yeah, you can get a pretty good tagging system on that. But for a lot of things, it's really hard to pin, or it may span multiple categories, and sometimes you got to pick one. It's a big mess. So this sort of user control, it's not really a good system, especially at the scale of Facebook. All right, I should add with that, I remember back in the 90s when the internet was starting to catch on among the ordinary people, they had this whole big promotion where they said, oh, one of the things you'll be able to do when you get the internet is you'll be able to custom build your own newspaper in the morning. You'll be able to check off topics that you're interested in, and then you'll have those articles brought right to you. Yeah, it doesn't really work that well. Okay, what happens again these days, to the extent that anybody's trying to do this, they try to tag news articles that are of local interest, or they make assumptions about you. In some cases, they may look at what you've clicked on in the past, but usually it's pretty localized. You can still have that option to build your own custom newspaper structure, but the problem is it just doesn't work very well. There are too many topics and too much news. Having the users pick topics they're interested in, you're going to miss a lot. Okay. Next thing, presentation. So we can talk about that in terms of Facebook. For example, access Facebook through a mobile device with a small screen or a desktop with a very large screen. That's the obvious difference, but there's some more. So the first one, again, desktops obviously have much larger screen size. So what they say, more real estate, more area to put ads down. Another thing, the orientation is different. So a desktop is generally very big horizontally, but smaller vertically, whereas a mobile device, the way most people use it, is typically taller, but not as wide. So different screen orientation. So again, different layout for the application. Desktops will typically have much more local storage and computing power. So for example, apps that would run easily on a desktop might struggle a bit on a mobile device. And if you want to gather a whole bunch of images, for example, from all the different websites you go to, you can cache all of the browser data, right? So when you go to a page that uses a lot of graphics, but those graphics get reused on other pages, your browser is going to keep those so it doesn't have to reload them every time it reloads another page on that site. Well, again, on a desktop, it's pretty easy to do. But I find on my smartphone, which admittedly is not top of the line, it stores like a couple hundred photos at most before they start getting overwritten by other stuff going on. So again, not that much local storage. Last, much easier user input on a desktop, right? So the input mechanisms are different. On a desktop, you're typically sitting down, you've got a mouse, you can have a wide range of space to move the mouse around in, you have a keyboard, so writing a whole bunch is not an ordeal. On a mobile device, right, you're basically limited to swipes and taps, and you don't want to do a whole lot of that. Likewise, anything that requires you to enter in a whole lot of text is going to be pretty annoying on a mobile device. So, point is, same application structure won't be good, right? You want to have a mobile version customized for mobile devices and a desktop version customized for desktop users. All right. So one thing that plays into this, something called auto sizing. Okay, so auto sizing is the idea that you're automatically going to have your application expand or shrink to the available screen area. And there's two basic families for that, right? Responsive and adaptive. Responsive one responds to what the user does, right? It basically scales smoothly. So if you're making your screen bigger or smaller, the things that are going to be visible on that screen are going to change along with it. Whereas if you look at an adaptive screen, what's going to happen is that as the available screen area gets bigger, certain components will snap into place. So I'm going to bring us to, I'll do a whole screen thing, and then we can see what I'm doing here. Oh, we got a few questions. Not crazy, but yeah, we can talk at length about Facebook and how they pick the posts. Yeah, we'll talk about that afterwards. But there are a few things that Facebook does. Number figures out who you're most interested in, but also last I checked, they did a thing called your top 50 basically. So people that you were had your last 50 interactions with are substantially more likely to show up in your feed. And that's why Facebook can sometimes feel really streaky, like over the course of a few days or a lot of the same people over and over. So anyway, we're going to switch here to whole screen. And we'll see if this link is still active. Okay, so difference. Oh, you know what? I remember last I checked. Now I remember it wasn't active anymore. Well, we'll try it anyway. We'll see how it goes. Let's see. Responsive and adaptive design. Come on. Oh, good. Okay. So it's kind of funny, this one. We have a responsive container, and I'm gonna see with this. Right? As I shrink it down, it gets responsive. The adaptive one, it's kind of funny. It says it's adaptive, and it used to be, but they have since changed it so it behaves exactly like the other one, right? So the idea is responsive, it's going to change size smoothly. But what isn't responsive are these ads on the side. So I blow it up, boom. See, I have some ads here, right? This ad here, when I get small, the ad just goes away. Right, I just shrink in a little bit, boom, it goes away, I expand a bit, let it go back up, there it is, it becomes available. So these ads like adaptive auto sizing, adaptive containers, if there is space on the screen to show them, they snap into place. If the space isn't available, they instantly disappear. The responsive ones, they scale smoothly. Now, for this course, this is IDS 200, not, advanced web design. So all I'm saying with this, you don't need to know the difference between responsive and adaptive, but what is important is that you understand that these components will automatically change size when they're needed, right? So the way it plays out in Facebook, that's some stuff from office hours today, if you saw that. The way it plays out in Facebook, imagine if I'm trying to get the shape I want. Here we go. Here it is on a mobile device, right? And the way it looks on a mobile device, you'll probably have a couple things here, right? And some little things here. You can see what's going on, like friends and notifications, whatever. But the main part of it, right here in the middle, boom, there's your feed, right? So like maybe this one here is for chat, or not char, it's for chat. And this one here is for, you know, updates, right? Whatever's going on, Facebook wants notifications. We'll call those notifications. And over here, right, links to Facebook stuff. Okay, so if you want to see the other things, this is a menu. You can click on those bars and you'll have different options you can get to, right? And the reason is on a mobile device, small screen. Okay, mobile device equals small screen. Therefore, to reach all Facebook components, you need to basically go off screen. Okay, but on the other hand, on a desktop is going to be big. Ooh, ta-da. And not only on that desktop does it have space for the feed in the middle, right? It has a bunch of other options, groups, apps, right? Other stuff. Anything they want to, they can put on the side like that. Over here, I'm going to do these in green, right? Probably ads. They can show you all those. And up here, you know, maybe you got a little bubble up here for apps. I don't know. Your screen might look a little different from mine. And then over here, you got the same usual stuff, right? So, you know, friends, chat, notifs. Okay, and down here, the feed. Point is, desktop equals large screen, plenty of room to show all the basic Facebook stuff, right? And other apps might show on new screen. So for example, you decide to start a game of Candy Crush or something. Yeah, that's gonna, you know, to the space of your feed and some of this other stuff, but not everything. All right, so you're gonna design it differently. And again, let me add adaptive sizing. Simple, but it feels clunky, right? Because the changes are abrupt, right? Something changes, boom, right away. On the other hand, responsive sizing, more difficult, right? It's not something that you're going to easily do if you've never done it before, but it feels much better for the users, right? Resizes are very smooth. Okay, so there's that. Moving on. We'll do our slideshow then. Okay. So next concern, ads, right? And ads are a very big concern for Facebook because that's where they get most of their revenue from. Now, because mobile devices have small screens, they can't show many ads. Typical desktop ads, they don't interfere with the applicant use, right? The desktop screen has enough space to show a bunch of ads around the edges of the screen wherever it's going on. On the other hand, with a typical mobile ad, if it's going to be big enough for the user to see and notice, in most cases, they're going to interfere with their ability to use the application, right? So typically what happens, you have a big ad, blocks most of the stuff from the screen, and if the users want to get to the good stuff, they have to scroll past the ads or click on them to make them go away or wait for them to time out. So mobile ads, if Facebook forced the users to deal with that all the time, people might get sick, might say, ugh, I don't want to do this, right? Because that's what happens often on YouTube. If you want to watch something, there'll be an ad beforehand, right? And you'll be like, okay, I got to watch a few minutes of this so I can click past it. Now, people will put up with that on YouTube. They might not have put up with it on Facebook. So On Facebook, they said, you know what, we can't really viably do that. We can't block up everything with ads. So instead, what we're going to do, we're going to integrate ads into the feed. You're going to get a good mix of user content that you're actually interested in, and then various types of advertisements that we hope we can make money off of. Okay, and again, Facebook is tracking the post to ad ratio pretty closely so they don't drive people away. Everybody knows you got to see some ads somewhere, but at least on Facebook you can scroll past them instead of having to wait them out. Okay, next thing, clickbait. Okay, so we know what clickbait is. It's one of those casual definitions, right? Clickbait is something that exists for you to click on. Well, there's one sense of clickbait that just means, hey, here's, you know, a somewhat sensationalized link that says, wow, that's really neat. Let's check on that. But clickbait is a whole separate category of basically somewhat junky content. So we'll talk a little bit about that in Paint. All right, so we're going to draw a spectrum here. So there's our line. Over here, we're going to say non-content, zero value. Stuff that nobody's interested in, just all ads, okay? And back in the day, they had a name for this. This was what was called spam blogs, okay? So spam blogs were these super junky pages that were just packed with ads and existed because they hoped somebody would show up and click on them, often by mistake, okay? You don't see them too much anymore because the search engines have gotten pretty good at detecting them and not including them in search results. On the other hand, over here, right, we'll say high quality content, interesting to users, they repeat visit, right? So that's the only practical way to measure if something is of interest to users is if they come back. And then if they do come back, you say, well, I'm not going to judge whether this is good or bad art, but it's art that's good enough that you like it, so whatever. And some ads, probably, okay, but not a huge number, probably. Okay, so all those things, they have the somewhere in the middle here, right? We're going to draw this arrow. This is our junkometer. Somewhere over here, we have clickbait. Okay, and when we talk about clickbait on this, we basically mean somewhat junky content, although possibly interesting or entertaining, right? The classic one there, some examples of clickbaits, okay? You won't believe what your dog is trying to tell you. There's one. Or 12 reasons your girlfriend is going to dump you. You won't believe number 7. Okay? Or even 25 trips to take before you die. Okay? Things like that are clickbait. Again, often somewhat junky, right? But they can still be interesting, still be entertaining. Now, key attributes, right? Number 1, headlines or links promise a lot, right? They often make the news article sound a lot more interesting than it's actually going to be. I'm trying to move this. There we go. I grabbed it. Okay. They often promise a lot. Don't always deliver. Okay. Because maybe you will believe what your dog is trying to tell you. Or maybe out of those 12 reasons your girlfriend is going to dump you, you already knew 10 of them, and number 7 is old news, and the other 2 you're not even totally on board with. All right, and 25 trips to take before you die. Well, yeah, a few of them look interesting, but the other 22, meh. Okay, so that's one thing. 2, content often spread out over multiple screens so you see many more ads. Okay, so good content, high quality content generally means people are going to come back because it's worthwhile and interesting. They're going to see more ads that way. Clickbait, kind of junky content, they figure, yeah, you're never coming back. But since that's the case, they say they got you now, they're going to make you go through a whole bunch of pages and see the ads in order to see the whole article. Okay, and number 3, generally a pretty high ad count per page. Okay, you won't usually just have one ad. You'll have like a bunch of ads because they're going to try to cash in quick. Okay, so those are defining attributes of clickbait, and that's what we mean. So again, we don't want to judge what's good and what isn't, but clickbait visits often make you feel like you wasted some. Okay, that's the thing. If you read the article and you're like, oh, that was kind of a waste of my time, yeah, it was probably clickbait. Okay, so back to the PowerPoint. So how do they make money? Well, short answer, same as any online ad, right? The usual model, somebody clicks on the ad and the people who are running the ad, right, the advertisers, they pay the website where the clickbait is. So either people buy products and that's the justification for the ad, or sometimes clicks that lead to networks of other clickbait sites, right? And they figure they'll give you a tiny fraction of that. They figure any user who visits, say, a clickbait site has some probability of clicking on one of the ads. Maybe that visitor, on average, is worth about 10 cents. So for any click that leads to that network of clickbait sites, maybe they, kick back like a penny or two of that. So you can have that kind of mechanism going on. But at the end of the day, people aren't going to keep advertising unless somebody is buying something. All right. Now, we'll get into these technical system elements, and we'll cover a few of them. Content management systems, basically how content gets delivered and controlled, about who sees it. We'll talk about the basics of cloud systems, and if we get there, we may start in on these asset properties. I feel like we'll probably have enough time. So let's see how it goes. First thing, what is a content management system? Well, a content management system has 2 core components. Number 1, a content management application. So that's all the tools for adding, changing, and deleting content. So think about it on Facebook. Those are the mechanisms you use to make posts, to upload pictures, to get rid of pictures, all that stuff that's built into Facebook. That's the content management. That's the ability to inject new content into the system, right, and get rid of old content. The other part is the content delivery application, and that's a set of tools for permission-based content distribution. That simply means who gets to see it. All right, so on Facebook, it's mostly done by your friend settings. The default setting is typically you make a post available to all of your friends, but you have finer-grained control than that. You can say, I want to show this or send this message to just particular subsets of friends, or if you like, you could even make some stuff entirely public. But the point is, you have the option to do that. Now, the Facebook feed is based on what could be called a semi-public content management system. So there are some things on Facebook that are public to everybody, just so people can kind of know what they're looking for. And there's a lot of other stuff, of course, that's basic. So users, businesses, Facebook are all injecting content. Of course, the businesses want most users to be able to see their pages, right? They're pretty open to whoever signs up. Likewise, if Facebook is injecting its own content, right, some notification about a change in Facebook policy or some new feature that's coming up, sure, they want to make that public and available to everyone. Users, on the other hand, individual users are generally much more controlled about who they let see their content. So, content delivery is based on user-influenced rules for visibility and preferences, right? So, one thing that means you can generally control who doesn't see your posts, right? They only show this to a subset of users, but you don't have control over who does see your posts. typically only maybe 20% of people on Facebook are going to see. Most of the time, they won't rank high enough for enough users, enough of your to appear in all their feeds, right? Now, if you scrolled all the way to the bottom of their feed at the end of the day, sure, they'd see everything, but most users don't do that. So most users, unless you're kind of buddies with them, going to kind of lose touch as far as Facebook is concerned. There have been other issues in the past with Facebook influencing news article distribution, right? So this is something from the Washington Post during the election season of 2016. Basically, for conservative articles that were getting pushed down in the ranking system. They weren't getting widely shown on Facebook. On your point of view, I suppose that's either a bad thing or a good thing. I don't know. But the point is, Facebook does have internal people that are making decisions about this, about who sees what content. So you can do all the posts and things you want, but it's not a guarantee about who's ever going to see them or who is going to see them. All you really can have control as a user is saying, I don't want certain people to see this stuff. Okay. Now, the technical elements of that, well, maintaining a world scale set of mostly static would already be a challenge, right? If you had a giant pile of many exabytes of data like Facebook does, even if the data didn't change it, just making that available to everybody, for example, an image repository, that would already be a significant thing to do, right? But Facebook's problem is a lot bigger than that because Facebook has a lot of dynamic data concerns. Number one, there's a continuous flow of new, most recent data. So remember, Facebook knows that its most popular images are going to be ones that recently posted, right? So something like half of the images that are accessed on Facebook happened within, probably the last couple weeks. So there's always going to be that turnover in whatever part of Facebook's system is accessible. The most recent pictures are going to be there, and they're going to continuously get replaced by new, more recent pictures, and the slightly older ones, they're going to get pushed out into the other areas of the storage system. So that kind of churn is something that has to be aware of. Other things, real-time updates, comments, edits, Facebook has to manage a lot of that. If people are making posts and commenting on posts and liking or unliking and friending and unfriending, all that kind of stuff that goes on, that makes it a lot more difficult for Facebook. It's a lot to make sure that people are only seeing what they're allowed to see. Okay. Now, in terms of caching and replication, let's talk about that. So the worst case for Facebook's network is that content is very popular, but also very bandwidth intensive. That means it takes a lot of network traffic capacity to send it out. So imagine if there was some big celebrity interview. I guess Taylor Swift is popular these days. Imagine if she did some big interview and she told all of her secrets and 1 billion people all turned in at 8 p.m. Eastern time. That would be a very bandwidth intensive activity. Other things like video clips from a major sporting event, right? So suppose there's some oh my God moment during the World Series or the Super Bowl, whatever, and a lot of people are sharing that video and a lot of people are watching it. Yeah, that's going to put a big, a lot of stress on Facebook's networks, right? Because it's a lot of data all at the same time. Now, the good thing, most viewers won't watch content live, but they'll watch it staggered over time. So, for example, in the case of a Super Bowl ad, you won't have all 2 billion daily users show up in the morning and watch that ad, right? You'll have it all spread out over the course of the day. So, sure, it'll be busy, but it'll also be manageable. Now, Facebook's two-part solution, number one, caching, right? So we've talked about caching is just in general making something easier to reach is what we mean in terms of caching. So in this case, it would be typically storing popular content in RAM so it can be delivered very quickly on request, as opposed to storing it on an old mechanical hard drive where it would be much slower to access. Another thing, replication. So if Facebook only had, say, a popular video on one server of one data center, that one server would very quickly get overloaded, right? It wouldn't be able to service all those requests in time. So instead, Facebook makes many copies of the video. So like imagine somebody watch a video and the video is, I don't know, like a minute long, or the segments are a minute long each. So every time somebody goes to start watching that video, it's accessing it in in that drive, and that whole stream of data has to be pulled out before the next person can show up and watch that video. And even if you're serving multiple users at the same time, if they all had to do it sequentially like that, it would feel really awful, right? It would be really slow. You'd like say, I want to watch this video, but it would be like another minute before you could watch the next segment. It'd be a big hassle. So instead, they make many copies of the video. So anytime, so suppose you have 100 copies of it on different servers at a data center. Whenever a user clicks on they want to watch this video, they're going to get connected to a server that's ready to serve up that video because either nobody's watching it at the time or the previous user is just about finished. Okay, so caching and replication, those are basically the techniques that Facebook uses to serve up data-intensive services very quickly, especially streaming video. Okay, so cloud. Cloud, you have an idea, is a giant system with many hard drives, solid state drives, whatever, a tremendous amount of storage capacity. Now, Facebook has way too much data to store on a single hard drive or computer, right? So a typical hard drive would be like a terabyte. Facebook doesn't have petabytes, right? Doesn't have terabytes, doesn't have petabytes. It has exabytes. Each exabyte is a million gigabytes. No, sorry, million terabytes. So a very large quantity of data. And Facebook has, quite a few exabytes of data. So there's no way that you could store all that data on one single hard drive, one single computer, make it accessible for everybody if they're all million users. In particular, read and write requirements, right? If every user had to wait for everybody else to be done with whatever operation they were doing, nothing could ever happen. There'd always be this tremendous backlog of users. So I give a quick example of that in Paint here. So a hard drive, right? Typical hard drive. Typical hard drive has a seek time of, let's say, 5 to 10 milliseconds. Okay, that means anytime you ask the hard drive to find something, that's how long it takes to get the drive head to even start reading the data. And then another maybe 20 milliseconds or so to pull a megabyte of data. What that means, we can be charitable here, and we'll be a little on the slow side. So say about 25 milliseconds to pull 1 megabyte of data for a user. Or the hard drive could serve 40 users per second. Okay? Now, if Facebook has 2 billion users and they're all doing multiple things per minute, right? Clicking on stuff, scrolling, commenting, liking, etc. There's no way Facebook could even come close to keeping up, right? On one hard drive. They're not, it's going to be more than 40 actions per second. So instead, Facebook has millions of drives, and since they're operating in parallel, Facebook can keep up with the user activity pretty well, right? And we know this. If you use Facebook, there's usually not tremendous lag on doing anything. So whatever data Facebook is pulling from its system, yeah, it's able to do it fast enough. And that's because they have millions of solid-state drives operating in parallel. Even though Facebook is processing millions of requests per second, it has the capacity to deal with that. Okay, so the solution is this cloud system. So what happens, all of Facebook's operational requirements are broken up into pieces and allocated to computers. So for example, the ability to send instant messages, the ability to process new photo uploads, the ability to run games through Facebook's platform, the ability to make posts if I haven't said that before. Okay, all of those operational requirements get allocated to different servers. When users want to do those things, they get connected to whatever server they need to be on, and it gets handled. Okay, so you don't have everybody having this massive bottleneck by having all 2 billion daily users trying to access the same hard drive. Instead, right, they're allocated over a much larger set of machines. But the neat thing about cloud, all of these details are basically hidden from the users. So to us, it all looks like we go to facebook.com and we do stuff, and we have no idea which piece of hardware we're connecting to. All we know is our data gets to us pretty fast. Our requests get handled pretty fast. So cloud details are hidden from users, number one, for security, to make it harder for the bad guys to find out where to attack, and number two, for ease of use. It would be a big hassle if you had to pick what machine you wanted to use on Facebook and were your experience. It's actually much better. Facebook makes that decision, and we don't have to worry about it. They make pretty good decisions. Okay, so what is the cloud? Well, a cloud is a bunch of connected servers, a server network, if you will, or a server tier that has a shared interface, load balancing capacity, and some backup systems. So we'll jump ahead a bit. So this picture here, we see on the left, we see some stick figures doing things at flat screen computers. So a couple here, HTML, they're looking at web pages. This guy with an envelope, he's sending some email. They're all going through the World Wide Web there to facebook.com. Then a couple things happen here. So first thing, they're going to connect to Facebook. Once upon a time, this is actually a pretty old picture. Once upon a time, there was a load balancer as a separate piece of hardware that would allocate new connections to different groups of servers. That's what these cloud instances are, different sets of servers. But these days, it tends to all be built into one piece of hardware. So the firewall and the load balancer and some other equipment, that'll all be in one standalone thing. But the function is still there. Each user gets allocated to a particular set of servers where all their stuff is, right? The applications they're using, the data they want to get to. And as far as the user is concerned, yeah, they're just on Facebook, but as far as Facebook is concerned, they are directing particular users to a particular piece of hardware, to a particular server. Okay, so there's a shared interface. Everybody goes to facebook.com. There's load balancing, because you don't want one group of servers to be super busy while every other server is pretty idle. And then backup systems. There's a variety of backups in the cloud for everything like the applications that are currently running to the data that you have access to. So for example, when you upload photos to Facebook, Facebook makes replicas of them. If you're running an application through Facebook, that same application is available on some other machines. In case your server goes down, they can pretty quickly transfer you over to the other machine. Other features, cloud systems tend to be geographically distributed, and they tend to be highly secure because you have a lot of different users with questionable motivations all under the same roof. You know, if Facebook didn't have a good handle on security, or at least a reasonably good handle, people would stop using it. Okay, so you may be asking, what's a server? I mean, you have a vague idea that it's some kind of computer, but what is a server? Well, it is a computer that delivers requested content to network users. So, in one sense, a server is just any networked machine. If you ask the server to do something for you, it does it, and that's what serving is. So, like if you have a web server, you ask it for a web page, and it serves you the page. It delivers it to you. But in practice, servers tend to be much more powerful than the client computers. So the client computers are the ones we use to access Facebook. Reason is, number one, each of these servers could have to handle, you know, dozens or more individual users. So in order to run all of their applications and grab all their data quickly, yeah, it has to be a pretty powerful machine. The next point worth discussing, thick versus thin client and thick versus thin application. Okay, so I'm going to draw a picture to go along with this. We'll put this in Paint. All right, so imagine this is your typical three-tier system. We'll have a little bit more to say about the setup later. Okay, so here, my data is on one machine. Okay, this is the server that's running the application, so I'll call it application. and this is me, the client. Okay, so I show up to use Facebook. And we're all connected. I access my data through the application server. So for example, Facebook constructs my feed and shows me images from other people's posts. I don't know. That apostrophe is kind of a weird saying. From others' posts. There we go. Okay, so we understand that's the main thing that happens there. Now, thick versus thin client, thick versus thin application. So there's two questions. Number one, where does the application run? If it runs on the client, okay, it's a thick application, right? Most of the work is happening on my machine. So if you want to think about it this way, right? Me, server, right? From the perspective of me, most of the work is happening over here. This is the thickness part. Okay? If it runs on the server, or more generally, a different machine, it's a thin application. Okay, so thick application is running on your client, thin application is running on the server. And I will add, most Facebook apps are thin, right? They run on the server. You know this. We know this because you don't really install any separate applications to use Facebook. Okay, so you run them through Facebook. Number two, what are the machine's capabilities? Okay, a thick client has a lot of power, right? Lots of storage, CPU cycles. It can run fast. Okay, and RAM. Okay, so I'll say lots of permanent storage. Okay. A thin client has little power, right? At the extreme, think of an ATM screen that basically just echoes commands to and from the server, right? So you ask the ATM to do something, it sends that off to the server. The server sends a response back. It says, here, show the person this. It shows you the output. It's not doing a whole lot of computations itself. Okay, so these are our two things. A thick application runs locally. A thin application runs on the application server. Likewise, a thick client is a fairly powerful machine. A thin client is a fairly weak machine. How are these integrated in terms of business? Well, one scenario, thick clients running thick applications, right? If you have an application that's going to be run on the client machine, well, the client machine is going to need the power to run it. So that's one possibility. Or if you say the application server is going to do most of the work and the clients don't have to be especially powerful, well, then you're going to have thin clients running thin applications, right? Both of those make sense. Otherwise, you ask questions like, if you have thick applications and thin clients, right? they may not run well. Or thick clients running thin applications, why spend the money on that good hardware, right? Why spend all the money on that good hardware if it's not going to be necessary for the applications? Okay, so let's do a quick recap. We got this on a couple slides ahead. So, thin clients, again, relatively weak, like terminals without permanent storage. Thick clients are relatively powerful, like, say, up-to-date current desktops. Applications, a thin application, the work mostly happens on the server, and the results get returned over the network. In a thick application, the processing mostly happens on the client. And so generally you want to match the two, either thick clients running thick applications, that can make sense, or thin clients running thin applications. That makes sense. Okay. So cloud service, just close out this. There's not a whole lot extra to say, but I feel obliged to go over the slide. So in the cloud, you'll have a bunch of applications running in parallel. That is, you'll have a bunch of different servers, each running multiple copies of the same application, right? And typically, each server or a group of servers is designated to run one particular application. One reason for that is it's better security. Essentially, the data stream that's going to be going out of the server is going to look pretty similar. A bunch of different applications all running on the server, then there are a lot of differences, and it's harder to detect with automated security tools. The other thing, it's easier to back up, easier to recover, easier to manage quality of service, right? But the big one is quality of service. Imagine, and talk a little bit. Whoop. Damn it. Then it looks. Okay. Imagine if you have a server where 100 users are all using, I don't know, MS Word, right? Adding 10 more users, well, they'll probably be similar. So about a 10% usage increase, right? And that makes it easy to plan for quality of service issues, right? You can tell when you'll need more capacity and need to shift new users to a new server, okay? But on the other hand, if you have a complete mix, if you have a mix of 100 users using a variety of applications, right? From MS Word, low requirements, to, say, watching YouTube, which is high requirements, and you add on 10 more users, change might be negligible if they're all using Word, or catastrophic if they're all using YouTube, okay? So it depends, but basically you can see if everybody on a server is using the same application, they're probably going to have about the same data requirements, and you can tell when your server starts getting a little bit overloaded and isn't responding as well, okay? Mix of applications, then yeah, it's really hard to tell in advance. Okay. Now, well, let's take a pause for this. We're gonna see if anybody has any questions. I'm gonna restore this to my standard view. Nothing in chat, huh? All right, I'm gonna stop sharing for a moment. Any questions on any of that stuff? I mean, I hope it all makes sense, right? So we talked about a few things, right? We talked about auto sizing, talked about clickbait, okay, talked about basics of cloud setup, and the thing that was there on the last slide for cloud, the system will try to allocate new sessions, right, assign new users to servers in a balanced way. So servers don't get overloaded or stay mostly idle. Okay, if Facebook has a server up and running, it wants to have a decent amount of user traffic from it. So it's a lot cheaper to leave them turned off. Okay, questions on any of that? All right, then I'm gonna do the properties then. We're good. Okay, good. Somebody's good. I'm at least okay. All right. So we'll go back to our slides. And we're going to just discuss ACID properties. Then we'll call it a day. Okay. So relational databases, their big overarching goal, they want to make sure that any queries receive correct and current data. The essence of that is for any one request, there is one and only one correct answer, and that what gets delivered to the user. Okay, and it's implemented through what are called ACID properties. So the four letters, A for atomicity, C for consistency, I for isolation, D for durability. We'll talk about all of them. So let's consider a hypothetical example. Suppose you update your Facebook relationship status to "it's complicated." Okay? So first thing, atomicity. So in terms of ACID properties, atomicity means a group of related database actions is atomic. Either they all happen or none of them do. So for example, when you update your status, Facebook is going to keep additional replicas of that status, right? Everything they do in Facebook, figure there's a triple copy of it. So when it updates your one relation, it has to echo that to all the other replicas. If something goes wrong with a piece of hardware in there, the entire action is going to fail. It's going to spin its gears for a little bit and then respond back, say, sorry, something is wrong with Facebook right now. Please try again in a few moments. Okay, that's atomicity. That's one way to make sure that if there are a bunch of replicas of some data, they are all the same. Second one, consistency. So consistency means that actions are processed in sequence and according to database rules. The idea with that is you follow the rules of the database, and thereby you ensure that if you start with a consistent database, basically where all the data is following the rules, then at the end, all the data will still be following the rules. For example, okay, imagine if you unfriend someone prior to announcing your status change, right? The unfriending has to be processed first before the status change can happen. Otherwise, what could happen, right? I'll draw this in paint. I mean, you know what the alternative is. So we have these two actions. Number one, dropped friend, okay? Number two, update status, right? It's complicated. So what should happen, drop the friend happens first, this happens second, and so that friend should never see the status update. But what could happen is if this action spins for a while but doesn't complete, meanwhile, you initiated this action and it did complete, then what happens at the end? Well, what happens at the end, this friend sees this update, right, which you don't want to happen. So consistency, if you followed the rules, you would say, you know what, this thing has to be done before I can commence this thing because this second thing can affect the first one. Okay? So that's it. Actions are processed in sequence and according to database rules. As long as you follow that consistency, you'll be okay. Next one, isolation. So no database operations affect each other's directly. Each is executed the same regardless of what else is going on in parallel. Essentially, this means that operations on the same data don't interleave. And it's like consistency, but it's different. So let me give an example. We have this change, right? We'll do the same one, okay? Drop friend, and number 2, status update. Okay, so the friend should get dropped, the status update should happen. If they're both happening in isolation, this whole thing should happen first, regardless of what else is going on, and then this whole thing should happen second, again, regardless of what else is going on. But in practice, what happens, each of these, right, can entail multiple steps. So what might happen if we consider a problem, suppose the drop is executed on one data center, on one data center before another. Meanwhile, this status update is executed again on the other data center first, for whatever reason, okay? Because that's where the data is stored. I don't know. Okay, maybe the one data set is bigger, is busier, has a backlog of activity, whatever. Okay, so at the end of the day, what could happen? Remember, when you have multiple replicas of data, it shouldn't matter which you read from. Okay, they should all be the same. But if isolation is broken, then users can look inside the process, which should normally be hidden. That is, users should either see the state before the friend, before whatever, right? Before the friend drop or after the friend drop, but not an intermediate state where some data centers have the drop and others don't. Okay, that's isolation. And when you have isolation, you ensure that users are only seeing the correct and current data. Okay, last one. Okay, last one of these. Durability. Well, durability is pretty straightforward. The system is robust against failures. Basically, if some piece of hardware fails after a change was committed in the database, right, after your friend was dropped, then when they restore the system, that change will still be there. That's all durability means. So if you keep those 4 things together, right, if you say, I have atomicity, if there are multiple replicas involved in the change, for example, they either all change or none of them do. If I have consistency, that basically my database operations follow the rules of the database. If I have isolation, that nobody can peek inside an operation while it's ongoing. And last, durability, any changes are permanent. If you have those 4 things in place, you're going to get correct answers. The downside, as we'll get to on Thursday, is that it can make your system run really slow, especially at Facebook scale. Okay. So I'm going to return to our session here. Let's see, we got a lot of chat going on. We got some stuff. You can't see the slides? You can't see nothing? Oh, dude. I wasn't sharing. Here, I'm going to post it up now. So here are the, here's the paint. I thought I had the full screen here. This is the stuff on paint. Okay, so this was isolation. all that. So I'm going to hold it there for a minute. You can check that out. I'm going to go through back this other stuff. This was the drop friend and update status, right? So that was the consistency. And this was the quality of service stuff. Okay, so sorry we lost those things, but I'm going to go back through them again. Okay, that was the talk there about consistency, and this is the talk about isolation. Okay, apologies for that. Okay. All right, and the slides, of course, well, the slides are on Blackboard, so there you go. Anyway, I'm going to call this, so let's stop it. Questions on this stuff? I mean, we've kind of hit the end of our stuff. We'll do a quick recap of all this stuff at the start of Thursday, because I know, things went a little off there those last few minutes. So I'll do a quick recap on Thursday, but take a look. Hopefully it all makes sense. Questions on any of this? Okay. Well, it sounds like, I don't know. Don't have homework. Yep, no homework yet. That's right. You got to learn some more stuff about Access before you get the real homework. There will be one posted next week, which will be due, I believe, at the end of week 5. Yep. Okay. Well, that's time then. Have a good evening, everyone. We'll see you next time. Yeah. Okay.